Hey everyone, and welcome to today's Explainer. If you're an engineering student and you are currently staring down the barrel of your final year, just kind of wondering how on earth you're going to impress your grading panel, well, you are in exactly the right place. Consider this Explainer your ultimate senior to junior cheat sheet. Today, we're breaking down a standout, totally panel-dropping final year project, the SHL Audio Grammar Scoring pipeline. We're going to look at the code, the architecture, and exactly how you can build and defend a state-of-the-art AI that automatically scores the grammatical quality of spoken audio. Let's get into it. 0.806. If you want to make a rigorous academic panel instantly sit up and pay attention, you drop that exact number. This isn't just some random accuracy metric, okay? This is a 0.806 Pearson Correlation score on a Public Kaggle leaderboard for the SHL Labs Audio Grammar Scoring Challenge. Achieving a score like this in a highly competitive environment, it proves your project isn't just a toy. It's a robust, highly competitive machine learning engine. And by the end of this explainer, you're going to understand exactly how to build it. Okay, let's dive right into this. Here is our roadmap for today. 1. The ultimate project. 2. How the AI pipeline works. 3. Model evolution. 4. Running and customizing the code. 5. Acing your panel viva. And finally, 6. Next steps.
Section 1. The Ultimate Project.
As literally any senior will tell you, picking the right project is half the battle for graduation. You need something complex for sure, but it also has to be practical. And this project, it's the perfect formula. Why is it such a goldmine? Because it seamlessly combines cutting-edge speech AI and deep learning with a real-world automated grading problem. Evaluators absolutely love projects that solve actual human problems, like assessing spoken language fluency at massive scale. Plus, anchoring your work to a real Kaggle competition gives your methodology instant, undeniable credibility. You aren't just making up your own grading criteria here. You're competing against a global benchmark. Section 2. How the AI pipeline works. So, let's pop open the hood, shall we? The absolute heart of this system is something called wav2vec2-large. Think of this as the intuition of your AI. Developed by Facebook, this is a massive pre-trained transformer model boasting 24 layers and 1,024 dimensions. Instead of just looking at the volume or the pitch of a voice, this deep learning model converts raw spoken audio into highly complex, extremely rich numerical embeddings. It has basically learned to understand the phonemic and prosodic patterns of human speech. You know, the subtle pauses, the intonations, the actual building blocks of grammar itself. But we don't just rely on deep learning alone. Oh no, we use a powerful dual-engine approach. On one side, you have those deep speech features from wav2vec2 doing the heavy lifting for linguistic understanding. But on the other side, we inject traditional handcrafted audio features. We're talking about the absolute classics, MFCCs, pitch extracted via PIN, and the fundamental speech rate like onset counts per second. By combining the cutting-edge intuition of transformers with the hard mathematical rules of traditional audio signal processing, you give your model a complete picture of not just what is being said, but exactly how it sounds. So, the crucial question here is, what do we actually do with all these features? Well, this is where the magic happens. We use a stacked ensemble. We don't just train one single model to predict the grammar score. We actually train 4 different base models in parallel. LightGBM, XGBoost, a ridge regressor, and a support vector regressor. We evaluate all of them using robust tenfold cross-validation. Then, we take the predictions from those 4 models and feed them into a final meta-learner, which is another ridge regression model, to make the ultimate grammar score prediction. It is literally like having a panel of 4 different expert judges grade the audio, and then a head judge combining their opinions to get the most accurate final score possible.
Section 3. Model Evolution and Results. You know, grading panels don't just want to see a finished piece of code. They want to see your actual engineering journey. We started this off with version 1, using a basic wav2vec2 base model with simple pooling. And hey, that gave us a perfectly respectable score of 0.752. But then we engineered our way up. By version 6, we upgraded to the wav2vec2 large model, implemented multi-layer pooling, and added that stacked ensemble we just talked about. That's what pushed us to the peak Kaggle score of 0.806. And notice version 7 on here, we experimented with adding handcrafted features combined with tenfold CV and an SVR, and it actually dropped the score to 0.457. Showing this kind of iteration, both the big wins and the failed experiments, proves to an examiner that you were doing real scientific machine learning work.
Now, what's really interesting about this is a vital pre-processing design decision that you absolutely need to highlight. In machine learning, your goal metric dictates your entire pipeline.
This specific competition evaluates based on the Pearson Correlation coefficient. Because Pearson Correlation measures the linear relationship between two continuous variables, it performs significantly better when you leave your predictions as continuous decimals rather than, say, rounding them to whole integer scores. It's a really small detail, but explaining this shows the panel you have a deep, practical understanding of evaluation metrics.
Section 4. Running and customizing code. All right, let's shift our focus to pure practicality and get the keys right into your hands. The original author here, Joshko Hinkar, has made this repository incredibly accessible. First, you'll just grab the dataset straight from the Kaggle competition page. Next, you open the provided Jupyter file. It's called Notebook 60F03C62AEIBNYP right in Google Colab. From there, you install the dependencies listed in the requirements.txt file, and you can literally run the entire pipeline end-to-end sequentially. Seriously, you do not need a massive supercomputer humming away in your dorm room. You can just leverage cloud GPUs to get this running today. But hey, to truly ace your final year, you shouldn't just copy-paste, right? You need to customize this pipeline to make it uniquely yours. Try preparing a custom dataset of spoken audio files. Maybe record your classmates, or use a completely different language corpus. You can also dive into the Python code and add new handcrafted acoustic features into the pre-processing pipeline, using libraries like Librosa, or even swap out different base models in the Ensemble to see what happens. And the absolute cherry on top? Build a simple, beautiful web interface using Streamlit. Just imagine your panel uploading an audio file live during your presentation and seeing the grammar score pop up instantly. No way they aren't impressed by that. Section 5. Acing your panel Viva. All right, lean in for this one, because it's time for a mock Viva prep session. I guarantee it, an examiner is going to look over their glasses at you and ask something like, so why did you use wav2vec2 large over the base model? And why did you bother averaging all the hidden layers instead of just taking the final output? When they hit you with that, you confidently reply with exactly this logic. You tell them that the large model captures richer phonemic and prosodic patterns that are absolutely essential for spotting subtle grammatical errors. And as for the layers, well, the early layers of the transformer capture basic, low-level acoustics, but the later layers, they encode highly complex linguistic structures. So, by doing a weighted average of all the layers and giving higher weights to the later ones, you are essentially giving your model the absolute best of both worlds. Next up, they're going to test your machine learning methodology. They'll ask the ultimate generalization question: why on earth did you choose a complex 10-fold stacked ensemble instead of a much simpler single model? And boom, here is your perfect answer. You explain that using 10 folds instead of, say, 5 provides much more stable out-of-fold or OOF predictions. This actively prevents the models from overfitting to the training data. Those stable predictions mean your final meta-learner trains much, much more effectively, which leads to superior generalization. And that is absolutely crucial when you're dealing with relatively small audio datasets. It proves to the panel that you don't just know how to import a model, but that you actually know how to engineer a reliable, stable AI system. Finally, how do you close it out? You end your Viva by connecting your project to the real world. Explain that this architecture isn't just for a college grade. It's the exact foundation used for automated language learning apps like Duolingo, for intelligent interview scoring systems in corporate HR departments, and for scalable grading tools for educators worldwide. Leaving them with these high-impact, real-world applications guarantees you make a lasting, incredibly professional impression. Section 6, Next Steps. Okay, you now have the blueprint for a highly impressive AI project. Your action items for today are super simple. Head over to GitHub and search for Joshko Hinkar/SHL Audio Grammar Scoring to grab the code. Give the repository a star while you're there. If this explainer helped you map out your final year, make sure to connect with the community on LinkedIn and hit subscribe so you never miss out on our future AI project explainers. I'm going to leave you with one final thought to get your creative gears turning before you go boot up Google Colab. What unique audio data set will you plug into this pipeline to completely blow away your grading panel? Think about it. Get creative, start coding, and go crush that final year project.